In this video, we will discuss the chain rule. Consider the function h of x equals x squared plus x plus 1 quantity squared. We could compute h prime of x using the rules of differentiation from the previous sections. Expand h of x by computing the square, and then take the derivative. H of x equals x squared plus x plus 1 quantity squared, which is x squared plus x plus 1 times x squared plus x plus 1, which equals x to the fourth plus 2x cubed plus 3x squared plus 2x plus 1. Then h prime of x equals 4x cubed plus 6x squared plus 6x plus 2. But what about the function h of x equals x squared plus x plus 1 to the 100th power? We could use the same technique, but let's be honest, we would wind up spending at least a couple of hours trying to find the 100th power of this trinomial, and the result would be 200 terms long. And if instead we had the function g of x equals the square root of x squared plus 1, we can't simply raise this to a power. There is no way to simplify this function. But both of these functions are continuous over the real numbers, and thus both must be differentiable. Both h of x equals x squared plus x plus 1 all to the 100th power, and g of x equals the square root of x plus 1 are composite functions. They are composed of simpler functions. For example, h is composed of the simpler functions f of x equals x squared plus x plus 1, and g of x equals x to the 100th. So, and we can see that here, if we take g of x equals x to the 100, f of x equals x squared plus x plus 1, then h of x equals g of f of x, which equals f of x to the 100th power, which is x squared plus x plus 1 all to the 100th power. As a first step toward finding the derivative of a composite function h equals g composed with f, we write u equals f of x and y equals g of f of x equals g of u. Then, because u is a function of x, we can take the derivative of u with respect to x if f is a differentiable function, which gives us du dx equals f prime of x. Then, since y is a function of u, we can take the derivative of y with respect to u if g is a differentiable function, giving us dy du equals g prime of u. The derivative of h must be some combination of these derivatives of f and g. The chain rule. If h of x equals g of f of x, then h prime of x equals the derivative of g times f of x. The derivative of g of f of x, which equals g prime of f of x times f prime of x. That is, the derivative of a composite function g of f of x is equal to the derivative of g of x with respect to f of x multiplied by the derivative of f of x with respect to x. The general power rule. If the function f is differentiable and h of x equals f of x to the n for a real number n, then h prime of x equals the derivative of f of x to the nth power, which equals n times f of x to the n minus 1 power times f prime of x. This is just an application of the chain rule to functions h of x equals g of f of x, where g of x equals x to the nth power. For example, let f of x equal 3x plus 1 squared. Find f prime of x using the general power rule, then verify the result without using the chain rule or general power rule. Using the general power rule, f prime of x equals 2 times 3x plus 1 to the first power times the derivative of 3x plus 1, which is 2 times 3x plus 1 times 3, which is 6 times 3x plus 1. To verify the result, we first square 3x plus 1 to get f of x equals 9x squared plus 6x plus 1. Then f prime of x equals 18x plus 16. Plus 6, not plus 16. Factoring out a 6 from each term, we wind up with f prime of x equals 6 times 3x plus 1. Differentiate the function g of x equals the square root of x squared plus 1. First, rewrite g of x equals x squared plus 1 to the 1/2. Then g prime of x equals 1/2 times x squared plus 1 to the negative 1/2 power times the derivative of x squared plus 1, which is 1/2 times x squared plus 1 to the negative 1/2 times 2x, which is x over the square root of x squared plus 1. Differentiate the function f of x equals x squared times 2x plus 3 to the 5th power. We apply first the product rule, then the general power rule. F prime of x equals x squared times the derivative of 2x plus 3 to the 5th power plus 2x plus 3 to the 5th power times the derivative of x squared, which is x squared times 5 times 2x plus 3 to the 4th power times the derivative of 2x plus 3 plus 2x plus 3 to the 5th power times 2x, which is x squared times 5 times 2x plus 3 to the 4th power times 2 plus 2x plus 3 to the 5th power times 2x, which is 2x times 2x plus 3 to the 4th power times 5x plus 2x plus 3, which is 2x times 2x plus 3 to the 4th power times 7x plus 3. The book lists the answer as 2x times 7x plus 3 times 2x plus 3 to the 4th power, but these answers are equivalent. Find f prime of x if f of x equals 2x squared plus 3 to the 4th power times 3x minus 1 to the 5th power. F prime of x equals 2x squared plus 3x to the 4th plus 3 to the 4th power times the derivative of 3x minus 1 to the 5th power plus 3x minus 1 to the 5th power times the derivative of 2x squared plus 3 to the 4th power, which is 2x squared plus 3 to the 4th power times 5 times 3x minus 1 to the 4th power times 3 plus 3x minus 1 to the 5th power times 4 times 2x squared plus 3 to the 3rd power times 4x, which is 2x squared plus 3 cubed times 3x minus 1 to the 4th power times 15 times 2x squared plus 3 plus 16x times 3x minus 1, which is 2x squared plus 3 to the 3rd power times 3x minus 1 to the 4th power times 30x squared plus 45 plus 48x squared minus 16x, which equals 2x squared plus 3 to the 3rd power times 3x minus 1 to the 4th power times 78x squared minus 16x plus 45. Find f prime of x if f of x equals 1 over 4x squared minus 7 quantity squared. First, we rewrite f of x equals 4x squared minus 7 to the negative 2. Then f prime of x equals negative 2 times 4x squared minus 7 to the negative 3 times 8x, which is negative 16x times 4x squared minus 7 to the negative 3, which equals negative 16x over 4x squared minus 7 quantity cubed. Find the slope of the tangent line to the graph of the function f of x equals 2x plus 1 over 3x plus 2 quantity cubed at the point 0, 1/8. First, we calculate the derivative using the general power rule and the quotient rule. F prime of x equals 3 times 2x plus 1 over 3x plus 2 quantity squared times 3x plus 2 times 2 minus 2x plus 1 times 3 over 3x plus 2 squared, which is 3 times 2x plus 1 over 3x plus 2 quantity squared times 6x plus 4 minus 6x minus 3 over 3x plus 2 quantity squared, which is 3 times 2x plus 1 quantity squared over 3x plus 2 quantity to the 4th power. The slope of the tangent line to the graph of f at 0, 1/8 is given by f prime of 0 equals 3 times 2 times 0 plus 1 quantity squared over 3 times 0 plus 2 quantity raised to the 4th power, which is 3 times 1 squared over 2 to the 4th, which equals 3 over 16. Finally, we'll do an applied example. Arteriosclerosis begins during childhood when plaque forms in the arterial walls, blocking the flow of blood through the arteries and leading to heart attacks, strokes, and gangrene. Suppose the idealized cross-section of the aorta is circular with radius a centimeters, and by year t, the thickness of the plaque is h equals g of t centimeters. And the area of the opening is given by A equals pi times A minus h quantity squared, square centimeters. Suppose the radius of an individual's artery is 1 centimeter, A equals 1, and the thickness of the plaque in centimeters in year t is given by h equals g of t equals 1 minus 0.01 times 10,000 minus t squared to the 1/2 power minus 0.001 t. Since the area of the arterial opening is given by A equals f of h equals pi times 1 minus h quantity squared, the rate at which A is changing with respect to time is given by dA dt equals f prime of h times g prime of t, which is 2 pi times 1 minus h times negative 1 times negative 0.01 times 1/2 times 10,000 minus t squared to the negative 1/2 times negative 2t minus 0.01, which is 2 pi times 1 minus h times 0.01 t over 10,000 minus t squared to the 1/2 power minus 0.001. For example, when t equals 50, h equals g of 50, which equals 1 minus 0.01 times 10,000 minus 2,500 to the 1/2 power minus 0.001 times 50, which is about 0.08397. So the derivative of A with respect to t is negative 2 pi times 1 minus 0.08397 times 0.01 times 50 over the square root of 10,000 minus 50 squared, which is about negative 0.027. That is, the area of the arterial opening is decreasing at the rate of 0.03 centimeters squared per year.